Good afternoon, everyone. I hope you are doing all right. So, we are talking about light, and although last time we said, okay, we talked about relativity, Einstein's theory of relativity, especially special theory of relativity. That theory was developed because light had a constant speed, and that constant speed to you know to let's say take account of the constant speed of light, Einstein had to modify that time can change for two different observer at two different frame of reference, and similarly length can change. Similarly, the velocity addition has to be modified and so on. So that was also kind of a story originated from the light. Okay. And of course, before that, we talked about interference of the light, diffraction of light. So that confirms the wave nature of the light. So if we want to figure out if something is behaving as a wave, what do? We check if it interferes, okay, by setting up something like two slits experiments. So we've been talking about light for a while, okay, and today is not much different. Okay, so we're going to talk about this property of light, that light can also behave as a particle rather than just a wave. Yes, we have seen light behaves as a wave because we talked about theory of interference, and light goes through the interference. So that means it behaves like a wave for sure. But in this chapter, we're going to look at least one experiment, and of course there are many experimental evidence that shows that light acts like a particle. So to get there, first let's learn about some vocabularies, that the way we use it here. Okay, so quantum and quantization. So what does that means? How do we use that here, right? So that's what we want to talk about first. So for example, let's talk about quantization of energy. So we learned that gravitational potential energy depends on height or its vertical position, right? So that's what we learned. So if we look at something like this, climbing or riding on the ramp, what happens? All heights are possible here. So for example, if it goes from 0 to 1 meter, so that means we can have any number of height we can draw, okay, and whatever value we like in between 0 and 1. So that means it is continuous. The value of energy is continuous here, okay. But now if we look at the stairs, something like this with these steps, and then what happens? If this is, let's say, reference 0, and this is, let's say, 0.1, let me write somewhere here, 0.1, and let's say this is 0.2 in some unit. So what happens is now you cannot have height other than this multiple of this 0.1. So this can be either 0.1, can be 0.2, can be 0.3, but it cannot be like 0.25. You cannot stand on a height at 0.25 in these stairs, in these steps. Okay, so now what do we see is the energy is not continuous. All values of energies are not possible. So what that means? That means only discrete steps are possible. So when we have something that comes in a discrete values, we may say, okay, it's a quantized. So for example, these days we don't use ATM as much as we used to use like few years back. So when you go to the ATM machine, what you see is like it says, okay, enter how much money you want in the multiplication of, let's say, $20 or something like that. So they can give you $20 or $40 or $60, but none in between. Let's say $5. Let's say, I mean, not in between 0 and 10, for example, $5 or $15 or $16 or $17, and so on. So this ATM machine is acting like some sort of, or let's say, giving us some sort of discrete values, okay, in terms of in the multiple of $20 bills. Okay, so that's what called a discretization, right? So we talked about the standing wave generated by, for example, string, vibrating string, or could be vibrating waves in a pipe, organ pipe, something like that. We talked about those two things when we learn about the waves, right? So when we look at those, like the pattern, so for example, here they are fixed here, so wherever they are fixed, we learn that they're going to be node, and then there is node here. So node is a point where there is kind of zero displacement, right? So these are nodes, and in between nodes, we call that point antinode. And then what happens here is that you have this, like let's say, when we find the wavelength by counting the length, let's say counting the number of nodes and on antinodes, and then comparing that with the length and writing the frequency, because frequency, let's say V is frequency times wavelength, so frequency is speed over wavelength. So what we see is it comes in some sort of discrete values or multiples, okay? And we saw these, and the frequency that we get in this kind of setup is n times the fundamental value. So for example, if this has a value, so the lowest value we call fundamental, right? So if it is 50 hertz, for example, then this this being second mode of vibration, this is going to have 2 times 50 hertz, and so on. So this is also an example of discrete values of frequency we are getting in this experiment. So yes, so that's how we can write the frequency. So we say, okay, the frequencies are quantized, discrete values. So when we have discrete values, we say, okay, it is quantized. And the smallest value is the quantum. Okay, that's just the definition of word. Now, what is quantum physics then? So to be honest, quantum physics is very, like let's say, very extensive the way we now know it, right? So if you are taking, let's say, upper division physics, then quantum physics could be just a whole semester. If you go to graduate school, you can have quantum related thing for several semesters. So it's a very long, like it's a very, let's say it covers now, we know so much about quantum physics that we can learn so much things using the quantum mechanics. So here I am trying to cover that in one class. So I'm not going to be doing all those things that I have learned about the quantum by taking classes in, let's say, my undergraduate, graduate classes, and then also my my PhD thesis also involves a quantum. Okay, so it's a very extensive subject. So here I'm just trying to introduce the quantum physics to you in one class to give you some idea what it means. Okay, so here what I'm saying is that, okay, there are certain things that comes with some only the discrete values. Okay, only discrete values. So when it happens, we say, okay, that thing is quantized. So now let's talk about one experiment that led to the development of actually, like let's say this, or let's say proof of quantum nature of light. So when we light a light bulb, or when we get energy from, let's say, sun, what happens? We get like, we can have light bulb that has different power. So depending on that power, we get all possible intensities, all kinds of brightness we get. Okay. So we can have very little bright, and then we can have a bit more bright and even brighter, and so on and so on. We can have uh, very bright light as well. Okay. So we can have very powerful light bulb. So that means based on what we observe from this light bulb, or the light coming from light bulb, we cannot see that quantized version, or the limitation of like what package it comes in. We don't know. We cannot tell based on just light we get from light bulb. And the sun is kind of fixed power light bulb. Yeah, kind of. I think I can say light bulb because it gives us light, right? And it is kind of round bulb. So that's that. So this kind of objects are also called a black body. So when we do experiment, what we can do is, okay, we cannot have like we cannot set up sun in our laboratory. So to describe how the sun and the sun kind of object that behaves, what we can do is we can set up a device that has a very small hole, and let's say the light can enter through that hole. But since this is a kind of round object and you can see it has a rough surface inside, what happens? The light that enters goes through multiple reflection by following the law of reflection. So by that time, what happens is it keeps reflecting rather than coming back out. So because of that, it gets absorbed. So the light contains energy, and energy gets absorbed. And when we keep shining with the light and it keeps getting absorbed, what happens is it becomes warmer and warmer. And once it has certain temperature, for example, T, uppercase T for temperature I'm writing, then what happens is it starts emitting energy that is proportional to the fourth power of the temperature. So what that means? So for example, let's say, uh, at the beginning, there is only 100 Kelvin, and you calculated some value of energy for that. Let's say this T1 is 100 Kelvin, and you calculated some energy here. And let's say that energy value is E. Then if temperature doubles, for example, T2, which is 200 Kelvin. Let's say Kelvin is the scale of temperature, by the way, like Fahrenheit. We'll talk more about that in another chapter. So what happens is now energy that this object radiates being proportional to fourth power of temperature. So what happened? Temperature went from T to 2T, means T4 goes from, T4 becomes 2 times T4. So that means this becomes 2 to the power fourth and T fourth. And I think 2 to the power 4 is 16 times 16. So what that means is now the new energy, for example, at temperature T2 is now 16 times whatever we had here. Okay, so this is called black body radiation. So when we measure the energy, for example, radiated by black body, and our universe has these ideal black bodies, for example, the stars and sun being our star. Okay, so they are emitting energy, and we know the energy or the light that comes from the sun, for example, or any source, it contains several wavelengths. Okay, so if we look at this graph, what we see is in horizontal line there is wavelength plotted, and over here is intensity. Okay, so what do we see here is that the we are, coming from higher temperature, sorry, not temperature, but the wavelength, the longer wavelength towards the smaller wavelength when we are looking at this. So let's follow these lines from the right side. Okay, so what's happening here is that when so the wavelength of the light that comes out of these we are plotting. So if we look at these all wavelengths and then plot something like that, and then also plot the intensity and vertical axis, what do we see? The intensity becomes maximum for each of those, like temperatures. So for example, if you have, for example, our sun has a temperature around 400 Kelvin. Surface temperature of the sun is around 400, not 400, sorry, 4000 kelvins, right? So what happens? If we go the intensity, which is basically energy coming out per unit area per unit time, okay? So the intensity first sharply increases as the wavelength decreases, and then after that what happens? It starts decreasing. That's what the experiment shows. But based on this theory we knew, it says, okay, if temperature keeps increasing, then the energy should just keep coming, at larger amount. So there is no restriction, and the intensity shouldn't be coming down for any wavelength. Okay, but here this experiment shows, okay, that's not the case. This equation is not so much valid if we go, especially, so for example, at, shorter wavelength. So here, among the visible, shortest one is like a blue and ultraviolet. Okay, so what happens is this energy does not follow this kind of expected increased in intensity as the temperature, as the wavelength becomes shorter. So shortest wavelength for visible light is ultraviolet, or let's say that's coming from the sun. Okay, it's hard to see ultraviolet, but we may see like a purple color. Okay, so what happens is that in that case, the energy is supposed to go based on this theory. The energy should keep going up higher and higher and become very large value, but theory or the experiment shows it comes down. Okay, so that means this theory is not valid for all the wavelengths. So this theory needed modification because that theory wasn't supporting the experimental evidence. So what happened is when light was quantized and the new formula was derived for the intensity of light dependence on wavelength or frequency. Remember, frequency and wavelength are related. What happens? You see that new theory now perfectly matches the curve as it is obtained in the experiment. So what that means? That means is that here there was a problem with the theory that we knew. There was a crisis, also known as ultraviolet catastrophe. Okay, so there was this problem with this experiment, and to solve that problem, had to come up with the new theory, had to introduce new idea. Okay, so that's how the science develops. Up to certain limits, it works just fine, but sometimes beyond certain limit, it may not work. Okay, so for that we need new theory. So that's what happened here. Okay, so scientist named Max Planck introduced this equation and said, okay, the energy comes in the package of this multiplication of some number. Okay, so this h is called Planck's constant. It has a fixed value. It is very small number though, 6.6 times 10 to the power negative 34. So it's a very small number. And this f is frequency. And remember, frequency and wavelength, they are related. So shorter the wavelength means higher the frequency and vice versa. Okay, so that's what. So by introducing this, of course, the formula derivation of that formula is not this formula, but the formula that describes this curve is a little involved for our class. So we don't do that, but just wanted to tell you that sometimes the well-known theory gets in trouble. And now we have to come up with the new theory. So that's how the science develops. Okay. So I'm not saying the old theory was wrong. So it was right up to certain temperature and wavelength. Okay. And what happens? It does not work for, let's say, shorter wavelength. So there was this crisis. So now the job of scientists is to, okay, now this theory is not working. So now we need new knowledge. We need new theory. Okay, so they start thinking about it and then propose several solutions. And then some solution works. And that's how the science develop. Okay. So to solve this dilemma, the solution was that the energy comes in a package, just like discrete values. Okay. So what is that discrete values? So if we want to calculate that value of that package, for example, then you can use wavelength, find the frequency, and then multiply that by h, and that's the smallest unit of energy we can have for that wavelength or for that frequency. We cannot have, let's say, a smaller value or in between two values. 2 times it's going to be either h times f or 2 times h times f, 3 times h times f. So when we have this kind of integer multiple, that's what we call discrete value or quantized value. Okay. So now, so when we're looking at here in this graph, so we have this wavelength, right? So you see there is ultraviolet, which it's not visible to our naked eyes, but close one, very close one is the purple color, and then comes a blue color, and then you see all those wavelength that's visible to us is within certain values. Actually, it is around, let's say, 400 to 700 in terms of nanometer. So there's this thing here, this width of this rainbow looking thing is in that. And you see, shortest wavelength is on the blue side and longest wavelength is on the red side. And others are in between. Okay. So this is like a dispersion spectrum we talked about when we looked at the how the white light breaks into different colors when we pass it through the prism, right? Because it refracts at different angles, and since for each color they have different refractive index, they bend slightly differently, and that different bending, when it passes through the prism, it separates into different colors. So here we are just trying to represent those colors with respect to the wavelength. So what's the value of those wavelength? That we call that, like let's say spectrum, and it goes from around 400 to 700 nanometer, and the longest wavelength is around 700 and shortest is around 400. So that's how I remember. Okay. And then comes the ultraviolet that has even shorter, and after ultraviolet comes the X-ray. X-ray has even shorter wavelength, and shorter the wavelength, higher the frequency, higher the frequency, higher the frequency, the single package, that minimum value we can have, is now gets higher and higher. So X-ray, UV, they have higher energy for each packet of that energy. Which one is one packet of energy? This much is one packet of energy. Okay, H times F. So since F keeps increasing as we go from this visible part of this to the ultraviolet, X-rays, then these are more energetic. So that's why ultraviolet light can cause harm in our skin. Okay, so that's why it's recommended that if you are outside, you put some sunscreen, because it basically uh, doesn't let this UV to directly get into our skin, depending on value of SPF. Okay. So now X-rays. So if you are doing X-rays, they put very thick metal in your body where they are not doing it, the X-ray. For example, often probably when you go for dental cleanup, once in a year, you may get X-rays for your teeth. So they are using that. So when they do it, they put some sort of, jacket with some metal. Why? Because it's even more energetic. It has more penetrating power. So it can, interact with our, let's say, tissues. And it may change that. Okay. And there are even more energetic in this spectrum. After the X-ray comes in what we call, what is that? Gamma rays. So that has even higher frequency or even shorter wavelength. Okay, so it is even more energetic. It can actually even penetrate through the, thick, not that thick, but little thick metals. The gamma rays can even penetrate through reasonably thick metals. So that's why this radioactive material, you have to be very careful. Why? Because they emit this radiation, which are, now we know the collection of these energy packets, very energetic, and all they are moving with the speed c. So they are very fast moving tiny bullets, and higher the frequency, they become more energetic, like a high speed bullet. Okay, so what happens? They interact with our tissue and they may damage our tissue. So that's why we have to be careful. And on the longer wave side, longer wavelength side, for example, this optical means visible, that we can see from red to, let's say, blue. And then we have infrared. It is kind of heat. If you are sitting next to fire, you feel warmness because this infrared radiation is coming from that temperature. Okay. Even our body can generate heat, right? And that is infrared radiation, we call it, because our body is also hot. Not as hot as light bulb or the sun, so that's why it does not emit the visible light. But it emits invisible light. We don't call it light. Rather, we simply say, okay, it's a part of electromagnetic radiation, and we call that infrared radiation. Okay. And then even the longer wavelength becomes now infrared, and then microwave. Remember, we use microwave radiation to warm our food. So inside that microwave, what's happening is there is a microwave radiation coming out and interacting with our food, especially the water content in the food. Okay, and then it set up in vibration and it becomes warm. And then even longer wavelength is radio wave. So this is microwave, and then radio waves. And we know all the communication, for example, phones, TV, all those uses radio waves. So they have longer wavelength, and they can have wavelength in kilometers. Okay. So these are all electromagnetic waves, and they have speed equal to c, speed of light, which is 3.0 times 10 to the power 8 meter per second, or 300,000 kilometer per second. Okay, all of them have same speed, but why they are different? Because they have different wavelength. And if we have wavelength between 400 and 700 nanometer, our eye can detect them and separate the color. So even the red colors, one red is not exactly same as another red. You can have different shade of red, right? So why that's the difference? Because there is slight difference in wavelength. So anyway, so light is wave, but just assuming light as a wave was not enough to describe this anomaly in this experiment. So had to say, okay, the light comes in a package, or the energy of light comes in a package, and this intensity is related to energy per second per unit area. So that means this is also directly related to energy. So that's why once this quantized version or discrete packet of energy was used to modify the theory, then this worked just fine. So this is one such evidence. Okay. Okay, so now I think here I have a question, but just realizing I did not start the clicker thingy. So go ahead, you boot the clicker. I'm also putting the clicker here. Okay, so now I'm starting poll. and you have a minute to pull on this. And by the way, that package of energy of light is also called photon. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got all of them. Bit more for D. So lowest energy in this list. So looks like yes, X-ray has the highest on these, and then ultraviolet, and then blue and green. So for example, if we go back here, what happens? Ultraviolet, and then blue, and then comes green. If there was red, red would have the lowest energy per photon. Okay, and by the way, this name photo means light, and remember electron, proton, charged particles, and then neutron, neutral particle. So we talked about this at the very beginning. Matter is made up of these, right? So all these have mass, and they are called particle, and they have this on. So this photo, once we realize it also acts like a particle, for example, the package of energy. See, I am trying to show you how to visualize light particles. So light can be a wave or also a particle containing that much energy. Okay. So when we say, okay, a particle, so we are making light particle or naming light particle by adding that on at the end, photon. Okay. So light particle. So each light particle has an energy. How much energy it has? That energy is given by h times f. F is frequency. So frequency can also be written as speed over wavelength. And since all electromagnetic waves have same speed, we can do this. Remember, I'm writing that from this formula. V is F times lambda. Means F can be replaced by V over lambda, but speed for the light wave is fixed, and we represent that by lowercase c, and that's why this energy can be written in terms of frequency or wavelength. Okay, so did I choose the answer here? Looks like I did. Yes. So now let's look at one problem. So I'm sure you have seen laser pointer. So how tiny light particles are? If kind of this is gonna give us some idea. Remember, 5 milliwatt. So our light bulb that we use in our room, if you are using LED kind, those could be like 10, 20, 30 watts, right? And if it is another kind with a coil, and then could be 100 watts, 60 watt, 200 watts, right? So that gives you some idea, like how brightness and the watts are kind of related. So lower the value of the watt we go, less bright it appears, right? So for example, a night light, they may be like 5 watt, not so very bright, right? Here is talking about 5 milliwatt, and each watt has 1,000 milliwatt. So that means 1 milliwatt is a thousandth of a watt. So why am I writing this several different ways? I'm telling you that, like, see how 1 meter is long, but thousandth of a millimeter is a thousandth of a meter is a millimeter. Now compared to that, 1 meter, a millimeter is very small. So similarly, 1 watt itself is not that bright, and if it is, uh, you know, milliwatt, that means it's going to be even less brighter. So what I'm saying is there aren't much power, okay, in this one. And it's talking about red light coming from laser pointer. Usually, the red are the low energy one, so bit safer laser than the, let's say, if you are using blue laser or green laser. So it says, okay, wavelength is 634 nanometers. Remember, I was saying red has a wavelength around 700 nanometer. So this is like somewhere there. So we are given wavelength 634 nanometer. So nanometer means there are, 1 meter has 10 to the power negative 9 meter. So meter and thousandth of a meter is a millimeter, and millionth of a meter is a micrometer, and billionth of a meter is, oh, what did I write here? I'm supposed to be writing 1 millimeter, and billionth of a meter is a nanometer. Okay, so to go from nanometer to meter, what we can do is whatever number we have, we multiply that by 10 to the power negative 9 meters. And it's asking for how many photons are there. If the power is 5, so number of photon per second, it says per second, so there is time here, or we can say, okay, time interval is 1 second. Okay, so power is 5 milliwatt, 5 milliwatt. Milli is thousandth, so that means we need to multiply this by 10 to the power negative 3 to get to the watt. Okay, so now it's asking us to find the number of photons coming out. So what do we know about photon? Each photon has an energy h times f. So if there are n number of photons, then it's going to have energy n times hf. Okay, and that's going to be the energy coming out every second. Okay, so power is energy per second. So since power is energy per second, right? It's the, we learned in physics 1. Did we use this in physics 2 somewhere? I don't quite remember at the moment, but anyway, so power is rate of energy change or rate of work done. So that's how we learn. And work done is rate of change in energy. Okay. So over there we talked in terms of kinetic and potential energy. Here we are talking about energy of light, but the definition is still same. So that means we know power, so that means how much energy is coming per second then. So energy and per second, if we want, we can say, okay, this is 1 second. So that means energy per second is the power, right? So to write energy, I think I can just do this, P times delta T. That way we can cancel the seconds and get the unit of energy. Power is joule per second. I mean, the watt is joule per second. So in this case, what happens? This is 5 times 10 to the power negative 3 times 1 second. And this is joule per second. So this cancels, so giving us just the joule over there. So delta E, energy per second that's coming out, is that many joules. So now we know energy coming out per second, but we want number of photons coming out per second. So each photon has energy equal to h times f. So if we have n number, so n photons has energy, just like I wrote here, it's going to be n times hf. So now, so if there are n number of photons coming, then in terms of this package of energy, the energy should be something like this. And based on the power, what we know, the energy coming out is this much. So that means these two must be same. So therefore, n times hf must be equal to that delta E, and that was this 5 point, okay, just let's write that. For now, we are solving for n, so that means it's going to be delta E divided by, so this is total number of energy, and this is energy of a photon. It's like saying, okay, there are 10 balls. Each ball has a mass of 10 grams. And let's say 10 ball, there is a bundle of, let's say, certain number of balls. And there is, let's say, there is 1000 gram when you collect all balls and then weigh it. And if each ball weigh just 10 grams, then how many balls there are going to be? To find that, you just divide that by that 10. So there are 100 balls. Same idea here. Okay. So total energy that's coming out every second is, we just calculated. So now how many number of photons coming out? So since we know each photon has this much energy, so it's like dividing by mass of a ball. Here we are dividing by energy of a photon. So that's the number of photons. So now let's write them down. Let's plug in numbers here. So change in energy per second is 5 times 10 to the power negative 3 joule. And then now H is like 6.662 or something like that. But let's just use that, 10 to the power negative 34. And then we have F. So to find F, oh, it looks like I need to write one more step here. Let me squeeze in. See, the wavelength is given. So we need to write this in terms of wavelength. So H, and frequency is speed divided by wavelength. So let's bring that wavelength fraction. A fraction goes up there. So I think we can use those numbers here. So wavelength goes here, 634 times 10 to the power negative 9. And this is H. And then now for C, we know speed of light is, so let me get rid of these. Speed of light is 3 times 10 to the power 8 meter per second. I haven't written unit for all, so I'm writing all the SI units, okay? Okay, so now what is this number? Anybody has a handy calculator there? So we have 5 times 634. So I'm separating numbers and the exponents. So 6.6 times 3 in denominator. So what are the exponents on the numerator? So negative 9, negative 3 is 10 to the power negative 12. In the denominator, we have negative 34 and positive 8. So that means 26. Yeah, 10 to the power negative 26. And we can combine these. So this becomes positive when we bring it up, and this is negative. So positive 26 and negative 12. Is that 14? How much is that? 26 minus 12. Yeah, looks like that is 14. So it's going to be positive 14. So 5.634. Oh, not 5.634. It's 5 times 634. And this is 6.6 times 3. I'm just copying that. And this becomes 10 to the power 14. So that's the number of photons coming out. So this is already 10 to the power 14. And here, if I were to estimate, see, this is 5, this is 6, this is 3, this is 2. So 200. So that means around, 2 point something times 10 to the power 16. So in the order of 10 to the power 16. So that very feeble light beam that's coming out, every second, how many photons are coming out? In the order of 10 to the power 16. And remember, 10 to the power 9 is billion. So I hope I did this correctly, estimated this correctly, but you want to verify that in calculator. If you did actually calculate that number, write that on the chat. So 10 to the power 9 is billion. And then now here, what we have is 9 and 7. So 10 million billion, 10 million billion photons are coming out from that, feeble, just 5 milliwatt laser light every second. So you can have some idea now how tiny amount of energy the H times F is. It's a very tiny, but nevertheless, it is a tiny package of energies. So we cannot have half times HF. Rather, we can have 2 times HF, 1 times HF, 3 times HF, and so on. Okay, so that's what it said. And this example kind of gives us idea how tiny that package of the photon or the energy is. Okay, so that's what it is telling us. So, for example, if we are shining that laser, it's not gonna like knock a rock off or something like that, right? But what happens is when we shine that in a metal surface, we know there are tiny electrons freely moving, almost freely moving on the metal surface. So when we fire that photons, okay, so when we shine a light, that means we are sending, several photons, right? Several photons. And then what do we get when we carefully do experiment? For example, if we were to connect this with wire and some sort of meter that can detect, so make a circuit out of there, then there are going to be current flowing. So that means there is electron moving. We see the electron moving. So that means the photons are photon has enough energy, may have enough energy to just take this out from the surface and give some kinetic energy so that it starts moving. Okay, so this process of emitting electrons by shining light on a metallic surface is called photoelectrons, and the current we call photocurrent. And in our daily life, probably you may have seen or used the solar panels. So solar panels uses this particular effect. Okay, so it's using this photoelectric effect to collect the electrons, and that is either directly connected to the power line or to a battery that can store that and then supply as needed. Okay, so that's how this is the working principle of solar panel. But when this was first discovered, nobody knew you can light up your whole home, drive car by collecting solar energy. I mean, using solar energy to collect electrons. Okay, so we did not know that at that time when this was first discovered. So to get scientific discovery into technology takes long, long time. Okay, so that's why there is no immediate payoff. And because of that, sometimes what happens when our government is in crunch, always there is need for more money, right? So in that case, they try to cut off the scientific innovation. And so they are not going to be immediate consequence, but in long term, that has a very bad consequences. So anyway, so looks like it's a good time to take a break. So once we come out from the break, so we will talk about what's the significance of this, experiment and the discovery in terms of learning about the light. So that's what we're going to talk. So for now, let's take a break. I'll see you in 5 minutes. I am back. Hope you are back too. So before break, we talked about, how the electrons comes out of certain metallic surface when we shine light. And there were some experimental observation. For example, the electrons came out instantly. The light gets in, electrons comes out instantly. Okay. So another observation is that how much current that flows. So current is basically, larger the current means larger the number of electrons coming out, right? So photoelectric current is proportional to light intensity. So that means light intensity means more energy falling on the surface per unit time, okay? And then you need to shine a light with certain cutoff frequency. All frequency of light does not generate the electrons out. So these three observations were a bit odd based on the knowledge of light at that time. And when I say knowledge of light at that time, what I mean is that the light was considered just a wave. Light as a particle wasn't that much known. Although, to describe the curve we just talked about, black body radiation curve, right? Max Planck used the idea of quantized energy. The idea of light being particle wasn't widely accepted. So now, when you try to explain this with the idea that light is a wave, let's see how these cannot be explained. So for example, so instant ejection of electrons. So what that means is that when we say, okay, just like, for example, there is water, we are trying to warm it, heat it, and let's say boil off the water. No matter how strong heat you apply, water may not instantly boil off. There is some time it takes to, water vapor to just come out. It takes a little bit time, okay? It's not an instant process. So similarly, if light was a wave, then the electron should take some time to absorb enough energy and then to come out. So there should be some delay. I'm not saying it should be in seconds, but there should be some delay in time, let's say in microsecond or nanoseconds or something like that. But what happens is the electrons starts coming out instantly. So that means the light that we are shining with is not behaving as a wave in this case, okay? Or the electron is not seeing that light as a wave. The electron is not responding with the light as if the light was a wave, okay? So another problem is the current, the number of current that comes out is proportional to the light intensity. So according to classical theory or the wave theory of light, what happens? More intense means more energy. So the electrons that's coming out should be more energetic. They should be moving faster with the more intensity. But rather what happens is when you shine this light with larger and larger intensity, they are not coming faster. Rather, more number of electrons coming out, which is also not, the electrons again not responding to the light as if it was a wave. So there was problem with the light being wave, this observation and that observation. And similarly, this one also indicates, why should there be cutoff frequency? Since according to light, wave theory of light, energy or intensity is directly proportional to the square of the amplitude. So you shine intense light and keep shining for longer time, this electron should wait and absorb, that, and no matter what frequency it is, it should have enough energy to come out, right? And it should come out. But it turns out, no matter how bright light you shine with, if it does not have a certain value of frequency, then it's not going to come out. Below certain value of frequency, it's not going to come out. So there is cutoff frequency, also known as threshold frequency. And you can say that in terms of wavelength as well, or you can say that in terms of energy. There is some cutoff energy. Okay? So that's what this is saying, and hopefully you got this idea that what was the problem. Okay? And then to explain this, Einstein borrowed this idea that energy of light comes in a package. That idea of the Max Planck. So energy comes in a package. E is h times f. Okay, it's written here. So it comes as a package, discrete. And that's when the photon became popular at that time. So Einstein used this idea of discrete light to explain this photoelectric effect and was able to explain it perfectly. Let's see how. So, according to Einstein, to say, okay, why there is instant ejection of electrons? So, Einstein is saying, okay, the light is not interacting with electron as a wave, rather it's interacting it as a like particle. So it's like hitting one ball with another ball. Okay, so what happens? One is touches, another one is starts moving, right? So that's the instant process. And so that means to get one electron out from the surface, it's going to take energy from just one photon of that light. If that photon has enough energy to pull it out from the surface and then give some energy, then it's going to come out. If not, then what happens? This electrons is not taking that energy. If it is less than a certain value that's necessary to get out, then what it does? Electron says no. It's like those kids, they want big candy. If you give small candy, they may not say, they may say, okay, no, no, I need that big candy. They might point on the store and say, I want that. So electron is acting something like that. I need that big candy, at least this big candy, otherwise I'm not going to take it. Okay, that's how electrons behaving. And what is candy for electrons here? The package of energy, H times F. And larger the value of F, larger the package. Okay, so now until there is sufficient energy for them to come out, they don't take it. That's how the Einstein explained that. So one by one transfer. So they don't take two small candies. Okay, so that's what that is. And the maximum energy of photoelectron is equal to the energy difference of the photon and the work function. So this work function, sometimes it's also written as W0, but I think I have written this as a E0 in the note. So this is basically E0 is that minimum frequency required. Okay, so just like saying, if the energy of photon is not enough, so see these electrons, although they are free to wander around on the metal surface, they cannot just jump out from there. To break them, this, although with a weak bond, to break them, from that weak bond, we need certain amount of energy. And that energy is called work function. And once the electron has enough energy, then it just comes out. So where does electron gets the energy from? The package of light or the photon. Okay, so that photon has to have that much energy or more. Less than that, it's not going to come out. So that's how Einstein explained that. And how fast the electron comes out, or the kinetic energy of each electron. Remember, kinetic energy is half mv. So this mass of electron and the speed of the electron that's coming out, half mv squared. And the maximum speed it can come with, with which it can come out, let's say, depends on how much energetic the photon is and how much energy is being used to just, you know, pluck the electron out, eject the electron out, and any extra energy from this work function is used, that goes into giving the speed or kinetic energy of the electron. So that's what this equation is saying. So this maximum kinetic energy can be written as in terms of mass and speed of the electron, and that is the maximum possible energy it can have. Okay, so in real experiment, what they do is they send them, they apply potential difference here. For example, if this electron is coming out, if you put positive terminal of a battery or some sort of potential source over there, then what's going to happen? It's going to repel that. Okay. So now when this is turned off, the electrons is running through the wire. But if you apply that voltage, then what's going to happen? This electron has to have enough energy to overcome this negative energy. Okay. And so that energy going to be E times V. Remember, energy of an electron when it goes through a potential difference of V or delta V is given by Q times delta V. Remember, that's the work done. And that is also equal to electric potential energy. So that's how we wrote. Okay. So that's what, so we can say, okay, that is charge is the charge of an electron and times the potential. Sometimes this potential is also known as stopping potential. And the stopping potential, when the energy due to stopping potential becomes equal to the kinetic energy, maximum kinetic energy, that's when the electrons stop flowing through the wire. So this kind of setup is used to measure, how fast the electron is coming out. So if you can measure that voltage, then you can calculate the speed with which the electrons are coming out. So that's how they measure it in real experimental setup. I think I may not have written this information in my note, but this is Einstein's equation, and that's how Einstein was able to explain this uh, observation that was, you know, that could not be explained by using the wave theory. So he had to use this photon theory or particle theory of light. Okay, so this is one experiment basically that tells us that light is behaving as a particle. Light has a particle called photons. Okay, so light particle, they're called photons. So this equation can be plotted something like this as well. So here you see this is called threshold frequency. If you are below this frequency, there are not going to be any electrons coming out. Okay. And then what happens? Once you go above that frequency, now see the kinetic energy is not zero anymore. So that means they are moving. Okay. For all these frequencies, they are moving, but there is a cutoff frequency that's called threshold frequency. Here, this I stole. Yeah, I was a bit lazy to plot this graph. So I stole from somewhere. So this pi is another notation for work function, but I'm writing that as a E0. Okay, so that's what that is. And you can write that as a HF0 if you like, where this work function is H times F0. Okay, so that is photoelectric effect, very important information. And remember how important it was? Einstein got Nobel Prize for this discovery. Einstein is famous for theory of relativity, but he did not get Nobel Prize for that because he died before that theory was, experimentally verified. But the photoelectric effect, it was easy to verify with the experiment. Actually, he was actually explaining the experiment, so it wasn't that difficult, right? So in this work, he got his Nobel Prize. So this is how important this photoelectric effect was. It verified that light acts like a particle. So, so this is the quantum nature of light. So now here is a question for you. Let's do 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So mostly B, but there are all there. So proportional to the intensity of light. Yes, that is correct. So B is correct. So according to this, particle theory of light, so more intense means there are more number of photons. Okay, large number of photons, and larger the number of photons, since there is interaction between 1 to 1 photon to electron. So if you send, let's say, 10 photons, then if all 10 of them have enough energy, then they can pull out or eject 10 electrons. If you send 100 photons, then they're going to eject 100 electrons. So that means now, according to this theory, quantum theory of light, intensity is not like I is proportional to A square. Rather, intensity is proportional to number of photons. Okay, so intensity is proportional to NHF. Okay, so now here is a working of solar cell. So in a solar cell, photons hit a thin metal coating and knock electrons out. That makes current. Assume the light wavelength is 386 nanometer. Oh, that seems to be on the blue side. So wavelength of light is 386 nanometer. And work function is that much electron volt. Oh, now it is not a joule. The work function E0 is 2.34 electron volt. So 1 electron volt is the energy of an electron when it goes through a potential difference of 1 voltage. So that means we can replace E by charge of an electron and this V by 1 volt. So because of that, what happens is 1 electron volt is 1.6 times 10 to the power negative 19 joule. Okay, the value is same as a charge of an electron, so that's why it's easy to remember. So we can basically convert this to the joule if we like. I think in this case we have to. So 1.6 times 10 to the power negative 19. And now it goes from electron volt to joule. So when we have this energy, very small amount of energy, what do? Is we write that in electron volt. Otherwise, see, this number becomes very, very small, right? But when we have to plug that in formula with the SI unit, then we have to do that in joule, right? And this is nanometer, so let's convert this into meters as well. 386 times 10 to the power negative 9 meters. So it says, what is the maximum kinetic energy? K max is what from the surface? So here we can use Einstein's equation. Equation of photoelectric effect. Equation. Why this sounds looks funny? Okay, K max is HF minus work function, right? So H and F is C over lambda because it's given in terms of wavelength. And then minus E0 is given as a number. So we can just use that. So now we know everything, so we are ready to plug in numbers. So H is 6.62. Let's say just 6.6 times 10 to the power negative 34. And C is 8 times, oh, it's not 8 times, it's 3 times 10 to the power 8. So that's a C. And then wavelength in this case is 386 times 10 to the power negative 9. And then E0 is that whole thing, 2.34 times 1.6 times 10 to the power negative 19. Okay. Let's see if we can write this in terms of 10 to the power negative 19. That way we can factor that 10 to the power negative 19. Yes, of course, now at this point you can, punch these numbers in calculator and get the answer. But let's see if we can do something a bit better here. So this is 9 and this is 8. So 9, when it comes up, it becomes 10 to the power positive 9, means it's going to be 10 to the power positive 17. I'm just looking at the exponents here, okay? And then there is negative 34. So that means it becomes 10 to the power negative 17. Okay, including that. But here we have 386. If I write this as a 3.86, it has now 10 to the power negative 2. When it goes up, it becomes, let's see. Oh, not that way. Looks like that's not going to make 10 to the power negative 19. It makes even smaller, looks like. So let's leave that as a 386. Instead, what we can do is, let's see, here, see, this is 10 to the power negative 17. So to make 10 to the power negative 17, we need negative 2 and 10 to the power positive 2 here because we cannot just multiply that. So that means this becomes 10 to the power negative 19. And now we have extra 100 in the denominator. So we need that. If we want, then looks like so looks like this number is becoming very small. I don't know. Let's see. HC over lambda and then minus E0. Hopefully I wrote E0 just fine. 2.34 times 1.6 times 10 to the power negative 19. Let's see if you get this positive number here, okay? 1734 is negative 17. So if we have 10 to the power negative 19 here, we can factor that out. Okay. So based on my, calculation in my head, I'm getting something like this. This times 10 to the power negative 19 here. But this has to be 38600 looks like. Okay. So am I doing that right? 9 and 8 is 17. Yeah, looks like that's what it is. But it's kind of not making sense much. So why I made this 10 to the power negative 19, now we can factor it out and get that. But I think, you can just punch in the calculator and get the number. Even after doing all this, I don't have the final answer here. So we need a calculator. So this is how we do this problem, okay? So I will leave this for you to, complete the calculation. Here, this number should be positive, but based on what I have here, kind of looking like a negative number. So hopefully I did not make mistake. So now, here is a question for you where you don't need to do all those ugly number calculation. Okay, let's do 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we're getting here. So we got all of them except E, a bit more for D. So blue has a longer, let's see, larger frequency or shorter wavelength, means it's going to have larger kinetic energy based on that. Okay. So if you use, most of the time what happens is red light may not eject the electrons. For most of the metals, red light does not have enough, like energy. A red photon does not have enough energy to pull the electrons out. So that's why it's a bit more, towards the blue. But in this case, it's saying, okay, red has a smaller frequency than the blue, so that means it has a more kinetic energy. Okay. So did I choose that answer? Looks like I did. So now, is light wave or particle then? So for that, what scientists did was they did some experiments. So for example, photoelectric effect shows light is particle, and interference shows light is wave. So what is it? Or is it both? Okay. If it is both, do they, act like wave and particle at the same times, or they just act one at a time? Okay. So that is kind of dilemma. That's the question that, scientists try to answer. So that's what I'm writing here. And basically, when they carefully did the experiment using this double slit, actually, even in a double slit, light showed its particle property. So that's what we are trying to see it here. So for example, how does particle we expect, how we expect the particle to behave when we have double slit. So for that, sands their particle, right? So for example, if you make two holes over there on a plank, for example, like a double slit, and then pour sand over there, then you expect, okay, there's going to be a pile of sand underneath that hole, another pile of sand underneath that hole, okay? And by the way, in the note, these diagrams are not there in the note. I was kind of rushing to finish that note, so I did not get a chance to properly, put the diagrams. Sorry about that, but the text is there mostly. So now, so that means if light is a particle, then we expect to see this, okay, like a sand. Sand shows, two uh, spot here. So similarly, in terms of light, we expect to see two bright spot like this, but we don't see this. We don't observe this. Rather, we observe this, and that shows the wave property of light. And this is, double slit experiment, Young's double slit experiment. We talked about that already in interference chapter. But let's see, let's slightly modify that, okay? So rather than sending, this whole bunch of light, what we can do is, see, if we want to send a photon of light, then it has to be really faint, right? A photon, so more photons means more bright light. So you want to control the light, like let's say brightness of the light or intensity of light until you have just one light coming out. So there are experimental setup you can control something like that. So what they did was they set up an experiment, double slit experiment. Now this time what they did was like they send one photon at a time for a long time. For example, see, if you're just sending just one photon, it is very, it's very dim. You can hardly see the spot. But in this sketch, each dot represents each of the, photon hitting on the screen, for example. Okay. So if you leave that for a long time, what happens? What happens? It shows you this again, it comes out 111, but if you leave that for a long time running through the, those that photon, one photon, another photon, and so on, for long enough time, what do you get? You recover this, just like, double slit experiment, right? So there are these bright and dark spot just like this, and there are some, random stuff in between. Those could be like, so for example, when you hit a ball, let's say through an opening, if it does not touch any surface there, it may go straight. But if it touches a little bit, it may bend. So we say, okay, those may be a little bit scattered one, okay? So now what they did was, okay, it is still behaving like a wave. So they try to, and by the way, so here, when it's coming one at a time, so is it coming through this wall or that wall, right? Remember, when we talked about wave, we send a plane wave. We said, okay, both of these act like a source of the light, and they come and interact or interfere. That's what we said. But now the question is, okay, if you are sending one photon at a time, then which wall it's coming from, right? So here, what they did was they did not care. They did not set up any, equipment to see which wall it is coming from. But they repeated that experiment by setting up, let's say, a detector. They are spying on the photon. Okay, so same setup, but now there is one extra device. There is eye. Okay, there is eye. Someone is looking, or this detector is detecting those photons. And when you do that, when you look at them, what they do, they don't produce this kind of pattern. Rather, they pile up like sand. So they are behaving like a particle now. So this is the dilemma the light is showing, okay? And it's very hard to explain what's going on. Here is one photon is passing through both hole or just one hole. And why they change their behavior when you are observing them. It's like, okay, if you are alone in a room, you may be, like maybe singing a song, humming a song, or something like that, right? But if someone opens the door and look at you, you may behave slightly differently. Looks like this electron is, I mean, not electrons, these photons are also kind of behaving something like that. So that is strange behavior. Okay. So probably if you have heard about Schrodinger's cat, so when they were trying to explain this dilemma, the Schrodinger, of course, who actually came up with the equation for quantum mechanics, like Newton came up with the laws of motion equation, F is equal to ma. There is equivalent equation for quantum mechanics. Of course, we don't write that equation. We don't do that here in this class, called Schrodinger equation. So uh, he imagined, okay, a cat being inside a box, and then there is something, let's say there is this poison that may come out. There is, let's say, so a container that contains some poison, and there may be some sort of event that triggers, release of little poison at a time. So when cat is inside and you're not looking, you don't know whether the cat is dead or alive. To make sure if cat is dead or alive, you have to look at the cat. And once you look at the cat, what happens? You'll know whether it is dead or alive. Until you look at it, what happens? It is both dead and alive at the same time. So photons are behaving something like that here, okay? So that's how basically, Schrodinger tried to explain this phenomenon with that Schrodinger's cat, explanation. So here, when you are not looking, it is both wave and particle, but when you look, then maybe it behaves like a particle. So that basically, that was the explanation of that. Exactly what's happening, hard to tell. Okay. So now there is a detector. When power is on, you get this. But if you were to turn off this detector, then what happens? It goes back to this pattern. So the detector has to be live, watching, working for this pattern to emerge. Otherwise, you get this pattern. So here is actual, those kind of experiment. I got this from one of the paper they published on it. Okay, so but this is for the electrons rather than photons, and electrons are behaving just like that. So electron, when you don't look at it and leave for a long time, passing through the the double slit, what happens? They have now this pattern, see, more intense in this region and not so much intense over there. Okay, so even the electrons forms this kind of interference pattern. So okay, light is behaving weird. So that means how about electron? Now electron, of course, we know it's a particle. It has a mass. But now it is also behaving like a wave. How do we know that? Because it's showing interference pattern. If something shows interference pattern, that means it is acting like a wave. So that means it's not just the light that acts like a particle and wave, but turns out even the electrons also acts like a particle and wave. Even the tiny atoms, not just the electron. If you shoot with the atoms, some experiment shows even the atom goes through the interference like a wave. So that what that means, atom is acting like a wave and it is a particle. So if we can expand that idea, we can say, okay, then this whole thing, everything can act like a wavelength. Everything has a wave. So that is the explanation of the universe, the quantum explanation of the universe. It is rather than, particle, it is also a wave, oscillation of energy, and so on. Okay. So that is kind of interesting. So here is a confirmation of, another experiment that showed how the electrons behaving like an X-ray. So this was done with the X-ray. Of course, we know X-ray is a wave, electromagnetic wave. And if you use that, you find even sharper image with the electrons, okay? So electron has a shorter wavelength, so they give you even finer image. So with this discovery, now they made an electron microscope so that you can see the atomic structure even better. Okay, so that's that, and here is the equation for the wavelength of a matter. If something is moving, it has a wavelength, and how much is that wavelength? That is h divided by momentum. This p is momentum, so it looks like I did not write that. H over mb, and this idea came from the scientist, so that's why the name de Broglie wavelength. Okay, and if you want to calculate that wavelength, then you have to write this, and mass, so this is electrons, so mass of electrons, and times the speed is this. 6.6 times 10 to the power 6 meters per second. Now you have wavelength of electron. So remember, this number is very small number, so that's why the wavelength of electron is very small compared to even smaller than the X-ray. Okay. And if you are running, you also have wavelength now. Plug in your fastest speed, your mass, and the value of h and calculate your wavelength. Yes, of course, it's going to be tiny, so that's why we don't detect. So that's why you don't see, we behaving like a wave. Otherwise, theoretically, yes, we may be behaving like a wave. So since we ran out of time, I'm not gonna, pull on this. So I'll let you go. Maybe I'll pull this on next class. Folks, if you have quick question, let me know, or else I'll see you next class for next topics.